Okay, so we're going to talk about neural networks, a topic which I'm sure you have heard about, to various degrees of depth. And there are, yes, too many comics to choose from. So this particular one, I guess the take-home message is, yes, your neural network or large language models can probably learn the patterns from any domain, including weird recipes. But after this lecture, hopefully you're convinced that the genetic algorithm is not the way to go for learning your neural network, or for updating the weights of your neural network at least. Yeah, the class have collectively done quiz 1. We're happy to see there are 287 submissions. The mean is around 73. So it's pretty much as expected. So these are, I would say, quiz are generally designed to keep you thinking and engaged in the class while giving yourself some feedback. So Josh Noon from the tutor team will join us after the main content of this lecture, and we'll talk about the quiz distribution and a few questions that most people got wrong. So stay with us until then, and that will also be recorded. I'm sure you don't need a reminder that assignment 1 is due next Monday. We have seen calls for help in Piazza and elsewhere. We do recognize that assignment 1 is challenging for most. So don't panic if you're one of them. So after today's tutor meeting, we will announce some extra support sessions for later this week, and hopefully that will help. So this is the main plan for today. We'll talk about neural networks, building upon what we know on linear basis, linear combinations of basis functions for both regression and classification. As said, that a lot of you would have heard of neural network in another class, somewhere in computer science, statistics, somewhere else, and so on. And the purpose of talking about this is to essentially build neural network incrementally from the chapters 3 and 4 that we have been learning about. So the content for this is mainly chapter 5 of PRML. I can update the sections later on, right? We will first define a neural network, talk about its general properties, including why we mathematically do not need more than 2 layers, but empirically you do. We all know that by now. And we'll talk about neural network training on how do we do parameter optimization. We'll basically take a general look at what optimization generally does. And then we talk about this famous algorithm called error backpropagation. We briefly mentioned what every single package implements these days, automatic differentiation, meaning that we never need to do backprop by hand, but the inherent mechanism is the same. We'll talk about regularization and what that might or may not be a good idea. Despite most of these terminologies you would have seen either in this class or in another class, we hope you take away something new anyway. And I'm quite confident that you will take away something new. So here we go. Equation 5.1 in the book is essentially, let's just say logistic regression in almost no disguise, right? So we have a weighted combination of features passing through an activation function f. And yes, logistic regression is a building block of neural networks. We can choose different functions f. in the classification lecture, we did strongly motivate the choice of the logistic function. But in here, we essentially say we're looking at generalized linear models with activation functions that are logistic and other things. And we make use of these ideas of recursive composition of the same computational structure. For those of you who has a computer science background, recursion is not a strange concept. And it is, again, as we see, one of the very practical and powerful concepts that helps machine learning as well. For those of you who don't know general recursion, then you could just treat this as an example of how combining simple looking things could build something powerful. So equation 5.9, because it's recursion, we read inside out, right? So the innermost layer is a linear combination of the input. We're just omitting phi here, because as we will show, we don't need it for neural nets. So we do a linear combination of the input followed by activation function h. And then we again do a linear combination in the second layer, hence superscript 2, of these first layer combinations, and then pass through another activation function. Right, so these two activation functions don't have to be the same. And what equation 5.9 shows is depicted in this simple picture that appears a few times in the book, right? So the input are x's. We denote there is an intermediate layer called z, where z is this, you can call it z of j, and x's are indexed with I. Throughout this lecture, one thing I would basically forewarn is so despite there's not a lot of new material, one trick of this lecture is the notation. Once we wrap our heads around the notation, everything should be straightforward. We'll talk more about that. But basically, there are three kinds of nodes. One are input, the one is the z's are intermediate, and y's are output. And more generally, we can index the x's with i's, z's with j's, and y's with k's. If there are more than these three types of nodes, then you could imagine these are just a snapshot of some three layers in the middle of a big neural network. All right. So the discussions is that they don't have to be fully connected. Despite in this day and age, if we have 1,000 neurons, we don't want to go about specifying which one is connected to which. We might as well fully connect them. So it says it can have skip connections too, which is used in modern practice, right? ResNet and its relatives. This third bullet point is still key, right? It requires the feed-forward structure. There is no directed cycles, meaning the computation of the neural network is done from left to right on this picture. And when I want to update parameters, it's done from right to left. If we have cycles, then it's going to be a lot more complex to do the computation, because if I wanted to compute the output, which in turn has feedback from the input, then I need to possibly iterate them before finding a fixed point about what the output truly is. So simplicity helps, and simplicity, like no complexity beyond necessity, also helps. The convention here is that the number of layers refer not to the number of weights, but to the number of not to the number of layers in nodes, but weights. So let's call this particular set of weights W of Ji, and it's on layer 1, and then these sets of weights are W of Kj, with a superscript denoting that they're on layer 2. Right. Okay, so we took a while to go through slide number 1, but I hope this will be useful. To quickly answer Taylor Chin's question, the short answer is no. If we decide to hold an in-person lecture, the reservation is now made on an ad hoc basis. I believe, yeah, the scheduling will try and place us in the like computer science and engineering precinct, but there is no guarantee that we'll use VIST. Right, where it is, we will announce beforehand. So Fei Yang asked, what is feed forward? Yes, there are a lot. So one thing about neural network is there are lots of names. What that means not exactly tricky, but just different names. So this is the feed forward function, right? It's called feed forward because the computation goes from the x's to the two y's via the z in the middle. I hope that helps. And feed forward structure or computational structure is indicated in this plot using this green arrow. I hope that helps. So basically, in equation 5.9, it's basically a recursive function, but it's a function nonetheless that takes x as input, and sigma and h are the predetermined functions, your ReLU, sigmoid, tan h, and so on. And w's are predetermined, or let's say a set of weights that are known. Or you can guess the weights and guess them random. But they are not. Okay. Yeah, why do we want such a structure? Right, what we just saw was, like in a simplified manner, this, right? X, Z, Y, and there are some connections in between. Something like that. So why is this good? This is good because such a simple structure can universally approximate any function, which is a very powerful statement. Of course, there's a bit more nuance about this, right? The criteria for universal approximation is what is called uniform convergence, meaning the maximum discrepancy between two functions shrinks to 0. So for regression, a two-layer neural network, as we said, right? So this is right. Layer 1. This is layer 2, assume weights. Two-layer network with linear outputs. Basically, the nonlinearity only exists here in the h function of the last page. Can uniformly approximate any continuous function on a compact input domain. Compact is informally think of it as Rn, or basically some continuous set that is connected to each other, to arbitrary accuracy, provided the network has sufficiently large number of hidden units. Meaning that if we don't restrict the width of the intermediate Z layer, so the width of this could go to infinity, could potentially go to infinity, then this network, the output y function can be any function, and this network can represent it. As an illustration to this, the book provides us figure 5.3, which is, I think it helps a lot to explain this rather counterintuitive phenomenon, right? So what it has is the intermediate nonlinearity is the tan h function. Change the highlighter, tan h function, and linear output units. And furthermore, this network only has 3 hidden units, like what we drew here. Yes, Shula, I'll get to the question a bit later. What this picture shows is here are four arbitrary looking but fairly different functions. One is the quadratic, the second one is the sinusoid, the third one is this V-shaped like x absolute value of x, and the fourth one is a step function which is not even continuous, right? And what has been so the training data are these 50 points. In here, when we say universal approximation, we're talking about training error goes down to 0. Yeah, if you have watched or been to the generalization lecture last week, you will know that means certain things and don't mean certain other things. But anyway, training error, caring about training error is important. So most of the neural net section, we're talking about training error. So the training data are these blue dots, and the training approximation lies almost exactly on these blue dots with some like caveats. In here, there's a bit curvy, there's a bit of error, but not too much, right? And you can show that these errors are sort of uniformly go down to 0. And the dashed lines show the three activation, well, three nonlinear units, right, after activation function. So the activation function of 10H, which is basically a shifted version of sigmoid. That's a bad drawing. I guess I drew it a bit too much like step function, but the sigmoid goes from 0 to 1, and the 10H goes from plus 0.5, negative 0.5 to plus 0.5, and the slope is exactly, well, the shape of function is exactly the same. Right, so you can see that the three later units somewhat looks like a 10H or flip 10H when say the weights are negative. And then what's remarkable is that just linear combinations of these three dash functions can generate these very different functions that we're after. It's easy to see in the step function because the 10H gets adjusted sort of relatively steeply. And it's just, for example, one step minus the other two steps or the other way around. But you can also kind of squint by mentally connect these three functions, three scaled version of scaled and shifted version of 10H to the quadratic and absolute and sinusoid, which is amazing. The trick is we cannot restrict if in order to universally approximate or get zero training error on any function, we cannot restrict the width of Z. Like so, to represent any function in the universe, we ideally need an infinite but countable number of hidden units, which is practically not easy, and which is also why you need deeper networks. One of the reasons why you need deeper networks. So going back to Shuliang Liu's question in the chat, yeah, we'll have a fuller answer of this in the middle of this lecture and by the next lecture. Basically, yes, if the number of Z is smaller than the input dimension, then we're essentially doing linear or nonlinear dimensionality reduction. So it's going to lose information and not going to be fully represent the full, like any arbitrary function, but there are sometimes good reasons for doing that. Okay, my hero's question is a good one. Okay, people are enthusiastic about neural networks. Okay, this is a whole separate topic in itself. For this class, we're going to assume that the number of layers and number of neurons are hyperparameters that we can somehow determine or do validation, like search over a validation set, as you guys all do in your, say, computer vision like evaluations. So this is also a topic that has lots of recent interest because there are so many different hyperparameters and it's sort of a big engineering effort and no principal way to tune them. One area of research, I'm just gonna write it down, that's relevant. even misspell Bayesian optimization, which or sometimes it's called auto ML. And sometimes, or more in the recent 3 years, it's called neural net architecture search. Yeah, it's known by all these different keywords. And you can even try and search for across different type of layers, like a residual layer, convolution layer, and so on and so forth. So the idea of Bayesian optimization is sort of model the objective, which are, let's say, training objectives or your loss or evaluation metric on the validation set as a high-dimensional nonlinear function, and then try and sort of do active learning in that complex space. One of the approaches or early approaches that has been quite successful is Gaussian processes, which we will cover the basics of in right after the break. The other two sets of keywords I won't talk about, you can go look for it. There are lots of interesting empirical work and some theoretical insight as well. I hope that helps. Right, so what have we learned that looks similar to this? We looked at the historically important perceptron, right? In fact, perceptron inspired these activation units with nonlinear activation or uncontinuous activation functions. And we did say in the perceptron section that the perceptrons were incorrectly labeled as not able to represent nonlinearities, despite multi-layer perceptron can indeed represent arbitrary nonlinearities. So in perceptron, the activation function is just a step function like this. But now we're looking at like value and many other garden varieties, right? So the claim is, hey, the activation functions H and sigma of a neural network are smooth and differentiable. Why do we want them to be smooth and differentiable? That is because we want to learn the linear weights. As we will see in the backpropagation procedure. So we have been practicing our vector linear algebra a lot in the last 4 weeks, or at least in the first 3 weeks. So I'm just gonna say, well, being able to having gradients are nice. Gradients of the end objective function, which we haven't told you about what it is. And having gradient everywhere in the parameter space is also nice. It's extra nice. Okay. So here are two, I guess, food for thought, right? So what if all activation functions are linear? What happens? If we just simply go back to the expression of the multi-layer perceptron, if these both sigma and H are linear, we also said then the linear combination of a linear combination is another linear combination. So if all activation functions are linear, this goes to one linear layer. There's no need to have multiple layered neural networks. Yeah, the second question has already been asked. So if we restrict the number of hidden units to be smaller than the number of input dimensions, or just restrict it like point blank, then we no longer have the universal approximation property. Okay. Okay, there are a bunch of questions. Let me. Yes, what indeed makes these nonlinear activation functions nonlinear? Because they are, yeah. So, so linear. Thanks for the question. Forcing us to be precise. A linear function, let's say, h of alpha times x will be equal to alpha times h of x. Right. So we're talking about linear function h. So if we take, say, sigma of x equals to something like this, sigmoid, then we can easily verify that sigma of alpha x is not equal to alpha sigma x, right, for a given sigma. For the given any given alpha, right? Why is this important? So despite this is the case, like things like sigmoid, they do have this shape, right? And all of these turning points are smooth. There is sort of a region in the middle. Sometimes this is called a linear region. Well, basically, they can be approximated reasonably well with the tangent line or the region in the middle, and basically the function value do change in here. So we want to be in this middle region and not on the tails, as we will see later today. So I hope that answers Jinhong's question. Qiyu asks, okay, ReLU is not smooth and differentiable everywhere. The gradient doesn't exist at that corner, but subgradients do exist, which is beyond what I'm going to talk about. Yeah, okay, UMR did have a short and good answer to this linear activation. So we are talking about, yes, activations and basis functions. One way to interpret neural network in light of what we just learned is that we can look at it as basically learning a variable, a flexible basis function that is sort of in a way tuned to training data. And hopefully your problem domain. What this also means, what we have been meaning in the last few slides is, so we don't need phi x anymore. Because now we are, like as in our chapters 3 and 4, we keep saying that, well, the feature function phi are kind of useful and they make the linear combination very flexible. In here, because two-layer neural network is fully flexible, even if we put in a fixed set of phi of x, we can always learn it. So here are some examples with, which I believe, 10H or sigmoid activation function. I could glean what from these figures. So if we have essentially two-dimensional input plus a bias term W0, we can see that, well, with zero bias and then emphasis, like a lot more weight, W1 is a lot bigger than W2, we essentially learn like a small step function-like thing, which looks like a sigmoid on one of the input dimensions, x1, right? So if we flip W1 and W2, we do essentially do the same thing on the dimension x2. And if we make them equal but opposite signs, we are learning a diagonal step function, right? So in this two-dimensional input plus bias, it's easy to interpret. Essentially, it's turning the direction of this sigmoid or soft step function in this 2D plane, right? We can also have, for example, a large bias term on top of this small step function. Then this will saturate the step function very quickly, right, and leads to this shape. So from the example we saw 2 slides ago about approximating any continuous function, you can now imagine this being able to learn any basis function, right, from sinusoid to quadratic to, well, quadratic with restricted domain and so on and so forth. So that is a pretty nice observation. In the book 5.1.1, they made us point about weight space symmetries. And interestingly, the book also said, well, these are practically not very important. I will argue the converse. It provides us a way of thinking about local minimas and why there are so many of them. So here's the thing. Given a set of input x, we just keep drawing this same picture. Input x, hidden layer z, and output y, let's say. And there's some connections that we randomly sprinkle, something like this. Assume it's fully connected. And these are m hidden units in the middle, and we denote the weight as basically the weight of the first layer and the weight of the second layer. The question is there another set of weights, W prime, that is different from W, that will always map the same input to the same output as W, which is a bit counterintuitive if you think about it, right? So we've been thinking y equals this function f of x, and f is powered or basically parameterized by these two sets of weights, which we call W. And maybe we just call it f. And then the same y, can the same y correspond to a different function f parameterized by W prime? So thinking about it, this structure has two sorts of symmetries. Source number one is what's called sign flips. So assume this only applies when we, for example, do +1 minus encoding, -1 encoding on the output, and also the activation function are, let's say, odd functions. Let's say we have 10H activation function. It's an odd function. It looks like this. It's sort of anti-symmetric around the origin. Then, and the 10H is in here. So if we flipped the sign of every single weight in the input, so if we flip the sign of weights in layer 1, and we also flip the signs of weights in layer 2, or subsets of layer 1 and layer 2 weights, then we get the same, essentially the same function, because we have more degrees of freedom than we need. So this leads to, because there are m neurons, we can do this independently for each hidden unit. This leads to 2 to the power of m weight space symmetries. And the second source of symmetry is, look, here are 3 hidden layer neurons in a hidden layer. It actually doesn't matter which one is called like the first neuron, the second neuron, the third neuron, and so on, right? So this is essentially permutation invariant. Meaning if I just renumber the z's and then correspondingly swap the weights between x and z and y and z, I'm still going to get the same function. So this one has m factorial number of different permutations or renumberings. So these two combined leads to 2 to the power of m times m factorial number of different weight combinations that lead to the same function. So not only there is at least one function that that represent the same input and output, but there are discombinatorially many different functions. So if we are doing training and tuning the weights, all of this 2 to the power of m times m factorial number of essentially weight configurations will lead to exactly the same objective function value. Oh, we'll get there in a few minutes. So because this semester we also talked about mixture models before this, and you're seeing it in the like doing it in the assignment, the same rationale, at least the permutation invariant one, also applies to mixture models. If I have a mixture of k components, then there is at least k factorial different local minimums or in a negative log likelihood space that correspond to the same mixture model, essentially. All right. So we have defined neural networks. Talk to you about the different names of feed-forward structure and activation function and so on. I reason about why things are this way. Now let's talk about training. And throughout this particular lecture, we're not going to touch generalization. We just assume we're going to try and train well and it will generalize, which is true to an extent, all right? So let's use 2 slides to look at neural network objectives. Well, building upon what we have been practicing a lot in chapters 3 and 4, here is a regression objective with linear activation unit at the output. It's basically, right, so we define this y of x comma w function according to 5.9 as basically this 2-layer neural net thingy. And subscript k correspond to the case output unit, which we'll get to in a minute. But if we like sweep k under the carpet, for if we have a single regression output, it's basically this, right? Y of xn comma w minus t of n, where subscript n is over the training data. Well, square loss, or basically the log likelihood of sort of a Gaussian output. This is very familiar. If we're doing classification, this converts to what's popularly called cross-entropy term nowadays, and we assume these Tn, right? Tn is either 0 or 1, uses 0 1 encoding right now. If, for example, the target has +1 or -1 encoding, then the objective looks different, as we'll see in SVM a lot. So as we already know, it's either term is active, but not both. Basically, one of either Tn or 1 minus Tn is 0, and the corresponding term is 0. All right, this is also exactly 4.90 when we talked about logistic regression. So inheriting this binary logistic output activation objective, we can also write out slightly different classification problem, right? The first one is called multiple independent binary classification tasks. So this represents what AlexNet, ResNet, well, basically, let's say image classification neural nets. So basically cats, yes and no, cars, yes and no, and so on. It's quite widely used. To go from one binary task to multiple independent binary tasks, and yes, cat and car can appear together, we simply add a summation term, which consists of summing over the k goes to 1 to big K output neurons, right? And everything else is the same. Another different classification task is called multi-class, meaning we can now choose only one type of class labels among the k possible class labels, right? For example, right, my 2-year-old at home likes to look at vehicles these days. From him, I now learned that vehicles in his world are classified into, let's say, trucks. They're very exciting. Cranes, diggers, cars, and so on. A vehicle cannot be simultaneously a digger and a crane. So what's different here is we still have this sum over k term, and only one out of the k terms is active. The rest are 0, meaning this tkn is one hot encoding. Zero, everything else should be zeros. Right. Okay, simple enough. Before we talk about training and how to do gradients in here, let's basically do a brief recap about what optimization in high dimensions look like. We already saw convex functions about 2 times in this class, so it just keeps coming back, right? Convex ball-shaped functions are nice. They are functions where the core lies above the function value. Examples for this are quadratic functions, as we learned in middle school, x log of x for x greater than 0. Is that right? Okay. And also for vector valued x transpose s of x. So the criteria for deciding whether something is convex is that the second, like roughly speaking, second order derivative greater than 0 or non-negative, where this thing can be basically derivative or the Hessian matrix if it's a vector, if x is a vector. Right. And we also saw Jensen's inequality. Don't need to dive into that in this lecture. So bearing in mind, we want to look at first and second order derivatives because the first order derivative tells us where to go to minimize or maximize the function. The second order derivative tells us the local shape around where, like a particular point. We were just talking about nonlinearity. And also because we said that this function's activation function sigma or h, or whichever thing we call it, is nonlinear, and it has many choices. So the thing about convex function is that a linear combination of convex function is convex, but a nonlinear combination of convex function is, in general, who knows what, right? So we are in this who knows what scheme in general. The universal approximation property actually supports many different activation functions, right? So for now, we assume that the error function E of W that we saw 2 slides ago, there were like many different forms, are in general non-convex. And we want to find the weight vector W that is a stationary point. So right now we're simply finding like a first order condition where we might be in the local minimum. There is actually no guarantee. There are many different other shapes, as we will see. A definition of a global minimum in a, let's say, arbitrary function in a continuous weight space is that a point W star is in which the error is smaller than any other error, E of W. The definition of local minimum is it's a point W star for which the error function is smaller than any other error in some neighborhood of W star. This is not very formal, but you can think of, well, small neighborhoods like this. There's no W star, right? So there's neighborhood. So some neighborhood, let's say, is correspond to this, right? There's a W and then there's some like circle around it, high dimensional circle ball around it. And the way we are optimizing is actually quite myopic, right? Because yeah, right. How do we think about this? In the sci-fi way, right? You think about U as being shrunken to the size of a dot on this high-dimensional landscape, and you don't know what the landscape looks like. For those of you who love skiing in like wild mountains, you might know what I mean. Is when you're skiing, your estimation of what the landscape truly is often not super reliable, but you do know quite well at where you're standing how to go downhill or uphill, right? And that is I guess that is the challenge, right? Assuming when you're skiing, you have a point to go, such as I need lunch in the shed in the ski resort. But if you are like a few hills over, it's hard to know directly what is the shortest path to the shed. And what you can do is can only locally go downhill and uphill. You can also have some idea about the local shape, meaning whether you are in the valley or on the hilltop. But that's about it. You don't know more than that. So imagine our neural network training algorithm is that here. What it does is what it can do is to find out a good direction, let's say gradient of W or delta W to go, and then try and decide how far to go. Right. Yes, when you're skiing, you can decide when you stop. So we resort to, the classic tool of Taylor expansion at a point W hat, right? In the neighborhood of W hat, we can expand E of W into the value of W hat. And then the first order term, basically, the difference between W and W hat times B plus the quadratic term. In vector terms, it's basically, right, the difference between W and W hat transpose times the Hessian matrix, right? The first order term B is simply the gradient of the error function. So this is don't think we have exactly examine Taylor expansion in this class, but generalizing from what you saw in Calculus 101, this is the vector version, right? So in calculus, you have essentially f of x at f of x naught, f prime of x naught, right? And x minus x naught, something like that. So that what we're staring at is simply the vector version of that. And the Hessian is a matrix, right? So let's say our weight vector is, let's say, well, we can index it however many ways. I'm just going to say this. Giant dimensional D, you can index the different layers, basically concatenate all our weights into a big vector, right? And then this B, this is a giant vector, so the partial of E, partial of weight, the first weight all the way E partial last weight. And this Hessian is a big matrix for those of you who haven't seen this. Basically partial of E of, well, the diagonals are the second order derivatives. Right, and then we have essentially the mixed derivatives. Which way does it go? I think I got it wrong. Do this again. Right, and so on and so forth. So this is a big matrix. The reason we write out the Hessian, we take the trouble to write out the matrix, is because computing Hessian is a problem for large networks, like for the ones that you train in computer vision and natural language processing. Because, you know, yeah, if you remember the weight vector, this in a lot of modern systems, this is in millions. A vector of a million long is kind of big, but it can be done. A matrix of a million by a million is big, and it cannot be easily stored in your one CPU or a single chunk of memory, things like that. And computing it takes a lot of time, right? So if a million is, like, we're talking about the low millions, 10 to the order of 6, then the Hessians will have order of, let's say, 10 to the 12 entries. No, you don't want to be doing this every single iteration. We'll talk more about that. So, yeah, the reason we talked about convex structures is that, okay, when the Hessian matrix is positive semi-definite, so this is the slightly formal notion, is greater than second order derivative greater than 0 condition, positive semi-definite. If you're more interested in these topics in more depth, take the advanced ML class next semester. But basically, here is the intuition, right? So when the Hessian is positive semi-definite, corresponding to this bow-like structure, something like this and this, then we're looking at a local minimum when a stationary point is reached. All right. If we don't look at the Hessian, meaning if we only have the first order condition of the gradient being 0, then we can be, well, simply at the maxima. We can be at the saddle point and the other structures that we have a picture of in pages. Okay. So this slide has lots of text, but it has important computational discussions, right? So some we already kind of hinted at. So the Hessian is symmetric and contains order of W squared independent entries. To see that it's symmetric is easy. Wj equal to, according to your Wj, Wi. Okay, that's easy. That means we have a giant W by W symmetric matrix, and it has like basically W times W plus 1 over 2 independent entries. So if we can use function evaluations only, and we do not know or do not explicitly compute the gradient of the function, we essentially need to gather the same order amount of piece of information by doing W square number of function evaluations, and then each of which costs order of W time. So the overall cost is even higher. If we don't use gradient and we want to evaluate a Hessian, this is bad, right? Just think W is in the millions, then we only want to do at most linear and ideally not quadratic. If we use gradients of the function, then one surprising observation is that evaluating a gradient also only costs order of W time. And it also provides us with W pieces of information. So if we want to evaluate the Hessian with the information of the gradient, the complexity is reduced, but it's still kind of bad. So this statement highlighted in blue comes from what's popularly known as the cheap gradient principle. What it says, due to Grewank, I believe he's German. He's recently retired, I think, but still maintains an active sort of page about this computing gradient, which is interesting. The computational cost of computing the gradient of a scalar value function is nearly the same, which is good news. And it's often within a factor of 5. I don't exactly know where the factor of 5 come from. If you go read about it, come and tell me. So it's nearly same as simply computing the function itself, which is great. And this is essentially the central tenet and the like go-to tool in numerical optimization, which underlies almost all the training we do. Right? Even when we do a linear algebra, like we need to do some numerical computation. So this allows us to quickly obtain high-dimensional gradients. So computing a million-dimensional gradient is not so bad anymore because it's simply the same as computing the original function. Yeah, so we can obtain high-dimensional gradients of scalar loss functions, which are subsequently used in black box gradient-based optimization procedures, aka your PyTorch, TensorFlows, and so on and so forth. So this is one piece of nice numerical like computation in modern machine learning. For those of you who have taken, say, machine learning or statistical learning in statistics, one differing foci of this class in computer science is that we do touch upon computational aspects, right? In math, more often you're concerned with, whether there is a convergent point or optimal point. And well, whether there is a correct inference procedure. And the computational aspect is often secondary, but I argue in modern machine learning, the computational and optimization view is quite important. So here's some like brief and imprecise exposure, but exposure nonetheless. So we talked about all the other geometric structures in high dimensions. So here's the picture of it, right? Right, so we have this mental picture of trying to do essentially skiing downhill in a ball-like structure. That's like the heaven of the optimization. We can see that if we have long valleys, there might be a global optimum, for example, here. And if we're just doing gradient descent, it can be quite bad, right? We're not basically it takes us a lot of steps to actually converge to the global optimum, because we're essentially going in a direction that's perpendicular to the global direction where the function goes down. And once we're near the bottom, we're just going essentially zigzagging and not approaching the global optimum, which is bad. Or in this case, we're just zigzagging even before we get to the right region. There can also be saddle points, right, which is a figurative name. So you can see that in this particular example, you can try to do a saddle point using a banded paper. I guarantee you it's not super easy, because in one of the dimensions, it's a global minimum. In the other dimension, like this perpendicular dimension, it's a global maximum. So it is the first order stationary point. But if you get to a saddle point, if you're just looking at the first order condition, you don't know where to go and you're like a bit confused. The second picture, I believe, right? So the simplest picture of saddle point is actually this one in one dimensional function. And this one is called the monkey saddle, which is a weird, another weird object. This other one is more intuitive. It's sort of a valley. It's like a bottom of your wine glass. It's a valley, but the valley is, there are multiple, a continuous region of global, local minimums. So anywhere you end up on that valley, like the valley can be long, or in this case, like a circle-like thing. Anywhere you end up on the valley, you cannot go anywhere anymore, and all the points on the valley is treated the same. So there are strategies for you to escape saddle points and diagnose valleys and so on, which is beyond what we can talk about. Right, so we talked a lot about the intuition of downhill skiing in the high dimensional space. Let's talk about error propagation, or backprop, as you all you must have heard of. For those of you who already know, then treat it as a refresher. For those of you for whom this is new, then let's take a dive. Basically, it's a very backprop is this very simple and neat abstraction that allows us to compute the gradients of multilinear network efficiently in a conceptually clean way. Okay, so we've established that we wanted to do gradients of error functions, compute the gradients of error functions, and we wanted to perform this downhill skiing operation on the wave space. That's the first equation. And a lot of you have done SGD, so it's basically the online version. We've already also mentioned it a few times in this class, meaning the error function is decomposed into a sum of error terms on each training data point, and we can just take a little bit of small steps that's based on information from, say, idealized one training point, but in practice a small mini batch of training points, right? Right, so if we have linear functions, doing backprop will be simple. So this is basically another view into our linear regression backprop. So the output is a linear combination of the input. We just denote this thing as y and k. And the error function is square error. And then the error function on the nth data point for the k's output is the following without the summation sign, right? And we just, the partial derivative for the gradient component on wji is simply this. Here's where the name comes from. So this is the error for output of the nth data point. And then J is either neuron component. and scaled by the input, right? As we saw in perception, this is the case. In logistic regression, it's kind of the case. So we've seen this. So there are two terms. The backprop trait refers to a computational gradient, and the forward propagation refers to essentially the feed-forward structure, the neural network computation that we've been talking about. So here is several terminologies. So we reuse the picture in the book. The trick for this particular section is that the indexing of the different variables essentially simplifies the notation a bit, but it sort of also sweeps under the carpet some of the complexities of the messiness of this computation. As you guys know, some of you know, right? The reason TensorFlow comes about is because a lot of these are tensor computations. And now we try not to use a tensor notation to cover it, basically, in the next 2 or 3 slides. So we can denote, basically, there are 3 layers of nodes. We can say the first layer is indexed by I. Give me a pen. The second layer is indexed by J. The third layer is indexed by K. So in our 2-layer neural net example, the first is input, the last one is output, and then weights is indexed by WJI and WKJ. This is what they will be called in the next 2 slides. And moreover, so on these intermediate nodes, so basically, there's this function. The output of this node coming out of here is the Z. But coming, just before the Z, we denote the activation A as the linear combination of the input, basically after applying the weights. And then between Z and A, there's a activation function H, right? The picture hasn't changed, and the first 2 equations we just saw. So right now, let's compute the back propagation for 1 layer. So this is no longer forward anymore. If we only have 1 layer, and we care about the error of a data point n, we apply chain rule. Basically, we wanted to compute the derivative for the error for point n on WJI, one of the W's. Chain rule simply says we compute the derivative of the error with respect to activation without the before the nonlinearity, and then the activation with respect to the weights. So look, this one is simple because of the linear function. So we know that the second part is simply Z of I, or the input value, as we saw on the linear slide a few. We basically are looking at some error term scaled by the input, right? The first term, right now we just treat it as a symbol because, right, so what is the derivative of the error at the end with respect to the activation? We give it a new name called delta J's. Right, so sitting on each of these nodes are, let's say, A3, Z3, and also delta 3. If you're actually doing this computation, you need to essentially compute and store all of these, as we'll cover. So the delta J's right now is just a symbol. We'll cover it in a bit because it's the key to recursion. And then the stochastic gradient on the nth data point is simply delta J times Zi. All right, simple enough. Again, this is notation trick, right? So by indexing these 3 layers as, again, I, J, and K's, we're not, we essentially swept away, these are weights of the first layer, J and I. So we omitted the superscript. Okay, now let's take this recursion forward. So what is this delta J thing anyway? because this neuron Z of J contribute to the subsequent calculation of, let's say, the output layer. On the output, we can also think of, well, there's an A of K, Z of K, and delta of K, the gradient sitting here. So in 5.55, this is the key right, this is the key backprop equation, which basically says, right, if I have K output units and the network is fully connected, then each of these output units on the same data point depend on this intermediate hidden unit Z of I, right? Because each of them depend on Z of I, right, when we do the derivative, and the error term is a summation of each individual error terms. We essentially sum over all the output units, and then again apply chain rule, right? So compute the error with respect to the activation at node K, and then this second term is the recursive term where we compute the activation at the later layer with respect to the activation at the previous layer. Right, so this one, because because Z of J is, let's say, H of AJ, then the path applying chain rule, it's H prime derivative H with respect to a activation at unit J, and again inside there's the linear term, and well, we set delta as a symbol, then we can just plug in the same symbol. And this applies to deeper networks, more than 2 layers. Right, to wrap our heads around, we essentially need to refer to the earlier definition of error function as summation of K, and like, right, the stochastic gradient version is just sum over K, and then the same term here. Yeah. And of course, this relied on the original definition of this 2-layer network. So that's it. Right, so this recursion just left it saying we wanted to compute this delta, and then we now end up with the delta of the next layer. And we can just, essentially, if we have more layer, we can just keep going, right? I thought it's worth sort of making argument on, yes, we should understand backprop. But before that, let me take Qinyu Zhao's question. It is a good question. Here we go. Let me try and copy this equation. Can I copy this? Okay, can copy this. Oh, anyway. So if we remember this particular equation of how the output is defined, so the goal is here is to explain why, intuitively, why this cheap gradient principle is true. A few pages ago, cheap gradient, yeah, here. Right, so roughly speaking, we have y, right, it's something sigma of w summation of, what is it again, right, wji h w, well, okay, I messed up. I think this should be k, otherwise I'm, kj wji sum over j x. No. Okay, this is a bit tricky. Right, no, y sub k is this function w j I xi. Okay, something like that. Right. So as we can see, so what matters in the computation is the multiplication, right? So in here, each component in W equals 1 to big W using the notation on this particular slide, goes through one multiplication, right? Addition don't count compared to multiplication. So therefore, the cost of computing the function is order of W. Right. I hope that helps. So the claim of the cheap gradient is that, well, since computing the function needs W number of multiplications, but computing gradient needs not more than 5W, then, well, they're roughly the same cost, right, in big O terms. I hope that helps. So there we go. We go back to, okay, we have, yes. So the core technical content we've pretty much gone through. In the last 10 minutes, there's a whole bunch of culture things, right? So yes, anybody can do deep learning these days, in fact. You just go import PyTorch and you're good to go. But the difference between people who really understand backprop and people who don't understand backprop is to be able to explain and diagnose why things work and why things sometimes don't work and being able to fix it. All right, here we go. Yeah, there is this Medium post by Andrzej Karpacki, who also did one of the first very popular deep learning course in Stanford, which is very good, right? So backprop and neural network in general is a very leaky abstraction, meaning just knowing the term backprop does not expose us to the inner workings of this, right? If we abstract away the learning process, and believing that I can simply stack arbitrary layers together and backprop will magically work, that's not happening. Again, this is one of, I think, the more popular XKCD comics about neural nets, but we should have a new sort of refreshed understanding of what's really behind this, right? A big pile of linear algebra and calculus, and behind that are these derivatives and activation functions. For example, for sigmoid function, we do not want it to be here or here because the derivatives are 0. The term for this is the neuron has saturated in either direction, and if the derivative is 0, if it's saturated there, then it's not going to change because it's taking no steps in that direction. Same goes with ReLU. We don't want to be here. The derivative is exactly 0 here. So non-zero derivatives are good, right? So this is the sweet region that corresponds to here. And in here, this is the non-zero derivatives region for the ReLU, and we also like that. So we'll talk a little bit more about this next time when we talk about auto encoders and stuff like that. But for now, saturated derivatives is one thing, one reason you should care about backprop. Also, there is the term called clipped gradients. You also don't want the gradients to explode. That would be bad. Yeah, so automatic differentiation. Well, basically, we're looking at a complex, recursively composed function for a neural network, especially deep ones. So how do we think about the inner workings of PyTorch and so on? For those of you who haven't seen, this is a 5-minute quick detour, right? right? So this is implemented is by schemes called auto diff or automatic differentiation. Very neat. Suppose we have a function, here's taken from the Stanford or borrowed from the Stanford course, which is not too complicated, but because we're good at writing derivatives, we know that this just manually deriving the derivatives can still be a pain, right? Because at the very outermost part of the differentiation or chain rule is this 1 over x, right? It needs to be like, and then the inside part will need to be expanded out. What you do here is you simplify this complicated looking function into the 4 different simpler components, right? You can this function, it actually there's only 4 different functions that goes towards it. The linear combination, the e of x, the x plus a constant, and the 1 over x. And then you construct computational graphs like this, where you essentially compute the gradients of these individual components and assemble them together. Note that okay. And some of these nodes are variables, some of these nodes are weights. Note that they're different. So, okay, let's stay at the sort of higher level. The takeaway for auto-diff, auto-grad, is basically we need to pre-program differentials of elementary functions. So it's probably no surprise to us that like a small collection of elementary functions can allow us to compose the derivative of many or almost all of the common functions we use. Of course, this doesn't include functions where like the closed form derivatives are hard, for example, the Gaussian like ERF function, and so on and so forth. Dependent, like, yeah, all of the auto-grad packages will have the common functions encoded, but if you're getting to the boundary of that, you need to look a bit more into it. And we can use chain rule to compose the stage-wise gradient, like in the flow diagram way. And then caching is important, right? That's why a few slides ago we were writing, oh, we need to compute and store A, Z, and delta for each node. Because as we can see, we need A's in both the forward backward paths, and then yeah, lots of values are reused. So in order to do that, in order to implement the cheap gradient principle efficiently, we need to store a number of additional things. All right, there's 5 minutes left. We can briefly talk about regularization. Right, the number of input and output nodes are determined by your training goal and the application. The number of hidden nodes is a free parameter that here already asked, how do we choose? So yes, we can either do cross validation or we can regularize. For example, using L2 regularization seem to help in like numerous examples that we looked at this semester. So if we're doing a 2 network, conceptually it's not that different from this, like because it's sort of composed the linear regression and logistic regression units and so on. What we learned there still applies, right? So, and L2 normalized regularizer looks like this. As we learned, it has a sort of Bayesian interpretation imposing Gaussian prior on the weights, which seem to be a good idea. As we also briefly mentioned in last week's generalization lecture, if we have a convex but not strongly convex objective function, then adding L2 makes it strongly convex function, which leads to nice looking bounds. In general, neural net functions, objective are not even convex, but right, I wouldn't make any overarching statements about the niceness, but just bear in mind that regularization also has a role to play when we talk about generalization, or maybe in this case, local properties of optimization. There's another, there's basically two more terms that are frequently used. One thing is called early stopping. We talked about single descent and double descent. This basically says across the training set and the validation set, you should monitor the error and stop when the validation error is at its minimum. All right, that's simple enough. And there are always also ways of incorporating invariances, either explicitly or using training data. Right? There's a long discussion in the book about that, but I feel like in the age of millions of neural net parameters, crafting individual neural functions so that they are invariant has not been seen as important in the past few years. Also, in last week's generalization lecture, we also saw the limits to building inbuilt invariances or explicit auto-regularization. In some tasks, learning tasks, they may not be that important at all. They still help, maybe only by a few percentage points rather than being make or break. It really depends on the training task and data and architecture you have. You can also do the Bayesian version of neural net, which is not too much different than the Bayesian version of regression that we have talked about. So I just leave it at that. So we only have 2 minutes left, but I thought I will, I don't know, give you a culture rant about, let's say the troubling trends of machine learning, especially terminologies, especially around neural nets. I kind of feel somewhat strongly about this personally, so I'm just going to impose it on you. So this particular paper, Troubling Trends in Machine Learning Scholarship, I just posted a link to that in the lecture channel. I like it very much. Zachary Lipton and Jacob Steinhardt are two of, let's say, the younger but very productive researchers. One of them works on fairness machine learning, Lipton, and Steinhardt works on NLP. Their paper covers a number of troubling trends, like not correctly attributing performance gains and confusing sort of explanation, causal explanation with some vague intuition that may or may not connect to the phenomena, and being overly messy, right? They have some very good examples. But what we are going to focus on in this class, which do not require going into the nuts and bolts in analyzing the algorithm, is simply the terminologies. As we said early on, there's lots of names in neural networks. Some of them are utterly confusing, and some of them mean different things. So briefly, there are three things: suggestive definitions, overloaded terminology, and suitcase words. So suggestive definition means a new technical term that's coined that has a suggestive colloquial meaning. And therefore, it may be sneaking connotation without the need to argue for them. For example, like many machine learning tasks, right? They're called reading comprehension, music composition. And let's say there are techniques or representations that are called curiosity and fear and thought vectors. So these are very, I would say, words that have broad implications in human abilities. By calling your algorithm that, you kind of were sneaking in a connotation that the algorithm, the particular representation is somewhat capable, somehow capable of, let's say, thinking, but they're really not. They're just encoding patterns, right? And also the claims of human level performance. For us, like who knows machine learning in depth, we should really sort of scrutinize this very carefully, right? Beyond human level performance in classifying ImageNet does not mean understanding the image, because there's so much more in the image. Then, well, actually, humans, we are kind of crap in classifying 10,000 different categories, including different breeds of dog. At least I'm pretty crap at that. Beating me is not a surprise, right? Okay, the second one is overloading technical terminology. For those of you who have done object-oriented programming, overloading your class is actually a very expressive way of crafting your software, right? In a succinct and nice way. But overloading terminology is bad, right? Deconvolution used to mean that if you have a blurred image from a satellite and you can recover the blurring effects from motion, weather, and so on. But now it just like being used to mean transpose convolution or what's called up convolution in neural networks, which is something entirely different. We're just changing dimension of input and output. So when people see deconvolution in the neural network related paper, you should really think about which meaning it is exactly. Another very commonly used word is this generative models. Okay, precisely speaking, in our classification lecture, we said generative models are models where you can manipulate or like generate x comma y from p of x comma y. That was the traditional way that it has been used up until the early 2010s. And then somehow GANs and VAEs came along and they just said, oh, yeah, I'm just going to call this models that generate pictures like generative models. What they essentially do is to perform conditional inference, basically sampling x2 condition on x1, which is the other part of x. And bending the term further, some of the discriminative models, which are supposed to be the conceptually other end, they are now referred to as generative models because they're, well, on account of producing structure outputs and so on. So this is very confusing. The last one is suitcase words. This term is coined by Minsky, again, pioneer of AI. So you can think about mental processes or true intelligence consists of things like conscious thinking, attention, emotion, and feeling, and so on. And things like interpretability, interpretation, interpretable models holds no universally agreed technical precise definition. That's why they are called suitcase words. If I say interpretable machine learning, it can mean lots of different things. And you need to be careful. And also things like generalization, like also has many different meanings. In, for example, last week's lecture, we referred to mean the performance on test sets and the gap between test and train. But it also could mean in the literature, generalizing from experimental setting to the real world, right? Some of you ask, oh, if I train a model in a large class, can I apply it to a small class? This refers to external validities, right? And this notion is also closer to transfer. These are different meanings. Anyway, so here are some cultural rants. We're done for today. We have looked at neural network, what it is, how to train, how to think about high dimensional downfield skiing, how to do error backprop and autograd in a snap, like nutshell. And we also talked about regularization and why it may not matter. So this lecture has sort of some conceptual connections with last week's generalization section. Hopefully it helps. Okay, so this is also to say that we are starting to build on the foundations we did in chapter 1, 2, 3, and 4. And you can see some of them at work. I'm going to pause here and see if Josh has come online to talk to us about the quiz. Josh? Okay, let me just quickly check. George is around. I am in my office. I could start sharing his slides, but I prefer if he does so. Meanwhile, everyone else can think about questions to ask us. All right. Okay, so we are actually going to do this in person. Luke asked, is assignment drop-in sessions, okay, is that going to be in person or online? I think given the spread of people in locations in this class, it has to be at least online. And then we'll see how it goes. We will announce that. We hope to have an in-person section, but we'll basically pull the tutors for their availability. Yeah. All right, so we'll stop my screen sharing that way. Right. No, I didn't. That's okay. We'll just. Yeah. That's okay. That's okay. We're just loading the quiz summary here. Let me just ask. So I invite Josh to come a bit closer, and Josh, you can, well, wait, let us load the slides. Huh? It's just slow. Yes, my computer is very slow. Teams is specifically slow too. Oh, yeah. Sometimes using two machines help. Okay, very nice. Let me do this then instead. Yeah, I have loaded. Share screen. Oh. This one. Yeah. Oh, great. So. Yeah. Okay, so Josh can start speaking. Give us a thumbs up or a question mark in case you can't hear.
Yep. Can everybody hear me?
Yeah, you should talk to the pad. That's where.
Yeah, right. So this is the.
Yeah, this is the mic.
Okay.
Yes, people said yes.
Okay, cool. Thanks. Give me a thumbs up. Right. So thanks everybody for doing the quiz. I think there's only one person who didn't do it last week. That's why we have this 0 marks in here. So this is a very quick recap of the quiz. I've seen quite a lot of discussions on Piazza about the questions you got wrong. So yeah, very good. I will endorse some of the answers that have already been discussed, and I will not go over all the questions in here, but I'll talk about ones that tend to confuse you guys the most. So so on the left hand side, you are seeing the distribution of marks in here. So the average marks for everybody was 72.97, which is pretty good, and on average, a little bit more than 40% of you guys got more than 80%. So I think that's a good indication. So you probably can see that the number of students who got 95 to 100, the last bar, is the highest. This is probably not very. Yeah, well done. Yeah, and also I think because we released the quiz for a week and we didn't have any timer for it, so this is actually quite expected. So on the right-hand side, you will see the maximum marks for each question, and the shaded bars are the mean, are the average mark for each. So yeah, so you probably can see the relative difficulty of each question. The first one, which is basically the question about EM, convergence, local and global convergence, is the easiest. So most of you got it correctly. On the other hand, the hardest question for everybody seemed to be question 6, which is actually quite surprising to me. But yeah, this question asks about the joint distribution and the the maximum likelihood estimator for X. So we're going to go through that question, right? So in the following, I will try to give you a solution to some of the questions that that confused you quite a lot. I won't go over the entire 11 questions in the quiz, but I've chosen a few. So this is a question about k-means, and lots of people seem to be confused in this particular question. The most popular answer next to the correct answer is it depends on the data set. So actually, this is incorrect, because if you set the number of centroids or the number of clusters to n exactly equal to the number of data points you have, you can drive the objective value down to 0. So that's the minimum you can get, right? So yeah, technically any number greater than or equal to n is a correct number. Right? So any question about this one?
Can just move on.
Yeah.
They will let us know.
Okay, yeah. So just stop me.
Okay.
Yeah.
Monitor there and take questions at the end.
Yep. Okay. And this question 5. So some people got it. Some people tended to be confused by what it means to have variance in here. So some of you posted a question on Piazza asking, "Oh, I thought variance here corresponds to the variance of a probability distribution," and that's actually not correct. So the variance that we're talking about here is the phenomenon where your training error and your generalization error, in this case the validation error, deviate or are very different, far away from each other. And so lots of people chose curve B has higher variance, but you can probably see very easily here that the curve that has a higher variance is curve A, because there's still a large gap between the two errors. Okay. Question 6. Yeah, so this one is the one that has the lowest average score among everybody. And so the correct answer to this question, you probably can see on Wattle, is that Q and M are independent random variables. So it's impossible to have Q and M as independent random variables. The first three answers to this question, A, B, and C, are all possible. You just need to put the right number for X in, put the right number for the question mark in, and you will have the exact probability. So they're all possible. So in order to prove that Q and M are not independent, you can prove using proof with. Oh, somebody raised their hand, right?
There is a chat. It's right. Yeah.
Yeah.
Yeah. Just talk and we'll pause.
Okay. Yeah. You can prove. For example, if Q and M, you can assume that Q and M are independent, and then that will lead you to a contradiction. And how do you do that? You can, you can show two cases. So remember, when Q and M are independent variables, that means their joint distribution is the same as the product of the marginals. So you can show in two cases where you have a joint distribution equal to the product of the marginals, and that will lead you to two different values for the question mark. So that would be a contradiction in this case. So that means that it's impossible to have Q and M as independent variables in this case.
Can you go back to question 5?
Yep.
Yeah, here. Why is this particular option not correct?
So a further increase in the training set could improve model B. So in this case, the training error and the validation error are already very close to each other. So the idea is if you train on if you train on a larger data set, so if you increase your current data set that you train a model on, the training error will sort of converge to some value, will converge to the generalization error, right? As we talked about last week, where delta gen goes to 0 as the training data set increases. But the thing is, delta gen is already very small in this case. You see the validation error and the training error are already very close to each other. So if you add more and more, the marginal or the added the added decrease in delta gen is going to be very small. So yeah, so that's unlikely to improve model B anyways.
Yeah, so you can think about improving model B in two ways. One is to reduce the gap between train and test, well, for generalization, which is delta gen. And we know from last week that, well, this is a bit beyond the quiz content, but right now you have a new interpretation for it. So delta gen will shrink to 0 if we have infinite amount of data. The other knobs we could potentially have is to change how what the model is, right? Which is not done by increasing the data set size. Change your hypothesis.
Yeah, I guess what I want to argue is that even though it's sort of getting close to, like, the gap between the training error and the validation error is kind of getting close to 0, but like unless you have infinitely amount of data, you still have like the gap between those are going to still be decreasing, right? So that's why I think this option could be kind of correct, even though the improvement is not very large. It's still improving model B, right?
Yes and no, right? So in contrast to the picture A, I remember the book also has a similar picture in the sense that comparing picture A and B, increasing the training data set size will not have much effect at all in B, right? You can argue with us on the epsilon amount of potential decrease in delta gen, but we do not believe you want to do that if you faced with the training curve. And also, please, I would say the mark does not really matter because 2.5%.
Yeah.
Yeah. So we stand by our answer here.
Yeah. So I mean, you do. Yeah. Your answer does make sense that it's going to decrease delta gen anyways, but because the deduction here is too small to the point that it would not make any practical usefulness at all. Yeah. That's a sort of point that we're trying to make here. Not want to get like super.
Yeah, that sounds fair.
Yeah.
Yep. Yeah. Thanks for the question.
Okay. Yeah. Good question. So question 6 we already talked about. Yep. Question 9. So this question asks about the difference between maximum likelihood estimation and maximum a posteriori estimation. And I think most of you got it right, but a lot of people, quite a number of people, chose either the second last or the last option. So what's the difference here? So if you remember from, I think, the first week or a couple of weeks later, you were introduced to two ways of fitting parameters to your data, right? The first one is MLE and the second one is MAP. And the difference between them is in MAP, you actually assume some prior distribution over your parameters. And for MLE, you do not. You consider it a fixed number or a fixed vector, and you're trying to maximize the data likelihood. But for MAP, you're maximizing likelihood times the prior, right? So that is proportional to the posterior distribution. But the point of this question here is that if you if you impose a uniform prior, that means the prior distribution, the prior density is a constant number for all values of your parameters. And that means if you multiply that constant with your likelihood, it's just proportional to the likelihood. So if you maximize the posterior distribution versus maximizing the data likelihood, they are exactly the same. So the last two answers should not be chosen because MLE and MAP are equivalent ways of fitting the parameters in this case. So they are all incorrect answers. The likelihood is constant for all trials, so this is incorrect, right? The posterior is constant for all trials. No, this is incorrect. So the first one is correct. And obviously, as I just mentioned earlier, because your prior is a constant number, then obviously your posterior distribution is just proportional to your data likelihood, which makes MLE and MAP equivalent ways. Right?
Can take that later.
Yep. Okay. So this is a question that asks you to interpret the coefficients in a logistic regression setting. So you might wonder why this number 16.2% comes up, right? Because it doesn't say it doesn't appear at all in question 11. So so the answers to this question, so your answers to this question tend to be sort of separated. So a lot of people chose 15% increase, and a lot of people chose 16% increase. So the correct answer is 16.2% increase. So that would be answer D in this question. So remember, in logistic regression, what you're trying to do is maximize. What you're trying to regress here is the log odds of your class 1, right? So if you have a coefficient of 0.15, then that means the coefficient corresponding to log odds would be 0.15. So if you want to transform that into odds, you have to exponentiate it, right? So that's why, so if you take e to the power of 0.15, you would have 1.162, right? So that means an increase in 1 hour of exercise will lead to 1.162 change. It's not the notes. Yeah. It's not the notes. Yeah. So yeah. So sorry. Let me say that again. So an increase in 1 hour of exercise would correspond to a 1.162 change in your odds. So that is 16.2% change. Right, 16.2% increase in your odds. So that's why it's not 15%. So you have to raise e to the power of 0.15. Okay.
Yeah, if you want to see where this is mentioned in the book, it's page 197 inside section 4.2. Yeah, where we haven't done the slides in a way that we can draw it. Otherwise, we'll. Yeah.
Right. Okay.
What? Oh yeah, let's answer the question. I'm gonna see if I can export this thing, but answer Fei Yang's question of
is it the case that curve A has higher variance, or is it the case that model A has higher variance?
Yeah, so going back to the curve, right? So here are a number of terms that are often overloaded. When we say model A, it could mean a number of things. It could mean, again, I can't draw. It could mean that it means a class of models, a hypothesis space, such as linear combination over, say, second-order polynomial kernel functions. That could be a model plus the associated algorithm to select the best single model out of this. Right. This will be like last week we mentioned algorithm A in the generalization lecture. That'll be a more general definition. The other definition is the model is, let's say if you're training a deep neural net, or if you don't want to train a deep neural net from scratch, you go to one of the model zoos on the internet and you say, let me download ResNet 156 and run it on my data set and fine tune it. So that set of coefficients of ResNet that's stored in the data file, that's also called a model. In this particular case, I think it's obviously not the same model, like not a single model we're talking about because of the varying training data sets, a single set of parameters that we're talking about. So therefore, it would necessarily mean it's a class of models with the training procedure and the implicit objective function that selects the best, let's say, set of W's for the varying data sets. I hope that answers Fei Yang's question. So it says, right, so in this case, model A has higher variance. It might mean like the hypothesis class has higher variance, or the objective function has higher variance, or the way we optimize the objective function has higher variance, it could, or a combination of these. Yeah. Okay. Jinhong,
could you please quickly go through why the expectation is a linear function of y in question 7? So yes, there's been an answer on Piazza about this. So if you want to,
yeah, sure, go.
2.114, I believe.
Right, the conditional Gaussian.
Yep. So if you want to answer this question, so there's been multiple people who already answered this question before on Piazza, so you can take a look at that. But you can also look at page 93 of your textbook from equations 2.113 to 2.117. And so to answer your question, why is x a linear function of y? You can take a look at 2.116, and that gives you a linear, the mean of x is a linear function of y.
Yeah, so basically x and y are jointly Gaussian. Y are, like the expectation of them are linear functions of each other. Or we know that the expectation of one is a linear function of another, which is the p of y given x.
Yep.
And then that implies p of x given y is like the mean of that is also a linear function of that of y. Yeah. Okay.
Yeah.
Fei Yang says, "Oh, what exactly is variance?" Back to this bias variance question. So going back to the book, yeah, this is a variance. The notion of variance is tricky, I should say. Just find it. And the reason that it's presented in the linear regression session is that the linear regression with synthetic training data provides a way of thinking about it in an idealized way. In reality, really, we stare at training curves a lot, but we don't have a way to analyze it.
So I think,
yeah, go.
Yeah, my understanding of variance in a model, in a curve like this, is when you have a large difference between your training loss and your generalization loss, right? Or validation loss if you're using a validation set. So, yeah, so the bias variance decomposition could appear in multiple settings. So in week 3, you probably have seen how we decompose the expected loss if we use the squared loss function into a bias squared and a variance term, right? So that is also an interpretation. But the variance that we're referring in here in this curve is the phenomenon that delta gen is a large number. So the gap between your training loss and your generalization loss is large.
Which is exactly the equation 3.4 he says. pretty much. Yeah, it's like over, let's say, potentially different random samples of the data set, how much do each, like what's the variance between each training loss and its expectation for different data sets. Yeah, the plots are, I guess, schematic and a bit stylized. I agree that, well, it's important to have these concepts, but it could be non-trivial to precisely map these concepts to the expressions that are quite long and a bit involved in the textbook.
Yeah.
Although thinking about these curves are a practical skill that I argue everyone should have. Going to sit here in case there's another question and slowly stop the recording.